So I'm here to talk to you about massless neutrino oscillation. All experimental data is consistent with massless neutrinos. The model requires three assumptions: the geometry, which we're using the vacuum wave function here to be that of the geometric representation of Clifford algebra. A scalar point, three vector line elements, three bivector area elements, and a trivector. So we've got this 1, 3, 3, 1 structure of the vacuum wave function. And to physically manifest, it requires that it has fields associated with the geometry, which we can get by introducing a coupling constant. The four fundamental constants that define alpha permit assigning geometrically and topologically flux quanta to the vacuum wave function's 8 components, and from that we can calculate the impedances of wave function interactions. And this is what governs amplitude and phase of the flow of energy. And we have the third thing is we have to set the scale of space. So the lightest rest mass particle, the electron, sets the scale of space at the electron Compton wavelength. So the wave function interactions are modeled by the geometric product, which you can see here is composed of two pieces: a wedge product that increases dimensionality and a dot product that decreases. And so we've got bosons and fermions here, and we're mixing the products, mixing them. This is dynamic supersymmetry. So we get this scattering matrix here that you can see by multiplying these two 8-component wave functions together in 6-dimensional phase space. You can see we're up to 6 dimensions here by multiplying these two 3-dimensional objects together. And 3 of the dimensions are space and the other 3 are phase. Time is the integral of phase. So if you do that integral, you collapse this thing to flat 4D Minkowski space-time. That's where the scattering matrix lives. And it's got the even algebra flavor eigenmodes you can see here, and the odd color transition modes for both the SU3s and the SU2s and the U1s. So the wave function we want to work with is comprised of the two photon components. You can see here an electric and a magnetic flux quantum on the skew diagonal of this flavor SU3, this color SU3 with the 8 color. The eight gluons, and so what we want to do is we introduce magnetic charge. This is the topological dual of electric charge. We've got the electric charge up here and the magnetic charge down here, both on the main diagonal. And the odd thing here is that the magnetic charge and the magnetic flux quantum, one's a one-dimensional object and the other 3-dimensional, they're numerically identical, but yet they're geometrically and topologically distinct. So this is one of the things that permits magnetic charge to offer topological protection to the photon and make it so difficult to see while it's still propagating at the speed of light. The left-handed universe, the algebra, the 3-component is not 3-component associative. It only works with one hand. It doesn't work with the other. So this is in the math, the origin of the left-handed universe. We can do the same thing for the muon, adding a degree of freedom to the 2-component electron to get a 3-component neutrino, a 3-component muon. And it looks like this. The muon decay looks like this, where we've got a muon that's a scalar, a vector, and an axial vector, and a neutrino that's a vector, an axial vector, and a trivector. They share a vector and axial vector. This is our V minus A coupling. So we can make an impedance network for basically all of the modes of the S matrix. This is a small part of it. But you can see the correlation between unstable particle lifetimes and nodes of the network that arises because impedances have to be matched for the energy to flow in particle decay. The neat thing about the neutrino is that it doesn't decay, it oscillates instead. And the origin of this we can find in the math, as I mentioned, but also we want to see it in the physics. What's going on in the physics that in Maxwell's equations, because the model is just QED with topology and geometry thrown in. But what if we look at this this reference 3 here, this might tell us something about what we know about that. So I hope I get to meet with you and talk with you during the actual workshop. Thank you.